In this video, we'll discuss transformers, which are special types of neural networks that are mainly used in large language models, such as ChatGPT. This was the original structure of the transformer that was first published in 2017 in a paper entitled "Attention is All You Need." A transformer can, for example, be used to translate from one language to another. This is the encoder, whereas this is the decoder part of the transformer. Suppose that we would like to translate this Swedish sentence "Jag gillar kaffe", which means "I like coffee". The encoder then processes this Swedish sentence, which goes into the decoder, together with the first two English words that have already been translated from previous steps, to predict the word coffee. Suppose that we would like to use a transformer to only predict the next word in a sentence of the same language. Then we do not need the encoder, which means that we use a decoder-only transformer. ChatGPT is, for example, a decoder-only transformer. This is the transformer that we will work with in this video to predict the next word in the sentence. Once the model has predicted the word coffee, it can be used as input to build a whole sentence like this. The transformer that I will use in this video involves word embedding and positional encoding. To simplify the calculations, we'll here just use a single head attention block and skip the feed-forward layer and directly use the output from the normalization layer into the final fully connected layer to predict the next word in a sentence. Inside a single head attention block, a number of steps take place, which involve the calculation of the Q, K, and B matrices. I will go through every step in this transformer based on a simple example. But first, we'll start to discuss tokenization, which is the process of splitting raw text into tokens. This sentence can be separated into the following tokens. In this case, a token is the same as a word. Each word or token is assigned an identifier, which means that each token is associated with a unique integer. These numbers are the ones the network uses to internally process the words. So, if the network were to interpret this sentence, it would write the sentence with these token IDs. Suppose that the network has predicted the following sequence of numbers that it wants to display for the user. It then converts the numbers to words or tokens, which are then displayed on the screen. I like my new car. Padding is used to ensure that all input sequences have the same length during training. Suppose that the expected input sequence length would be only 7 words or tokens during the training. If the model sees these 3 words as the input sequence, it would add padding like this. And the corresponding token ID sequence would then look like this. In language models, one uses masking, which is a way to prevent the model from learning from padded tokens. By using masking, the model will pay no attention to these padded tokens when interpreting the input sequence to predict the next word. Note that a word may also be split into 2 or more tokens to better interpret the sequence. So, now we know what tokens are and that they can be seen as words, characters, or parts of words. We'll now discuss word embedding, which is a way to explain the meaning of a word to a computer. Suppose that we have the following words or tokens and that we would like to explain the meaning of these words to a computer. Let's start by explaining how mobile these things are. For example, trucks and cars are mobile because they can transport things from one place to another. Cats and dogs can also move, whereas fruits and houses are not mobile. So, we give items that are mobile positive values. More mobile items will get larger values, whereas less mobile items will get negative values on this scale. This is called an embedding dimension, or an embedding vector, that describes how mobile the items are. Let's add a second dimension that describes if the items are eatable. Since fruits are eatable and are things that are not mobile, they will be in the top left corner in these two dimensions. A house is not eatable and not mobile, so it will be down here. Cats and dogs are normally not referred to as eatable, and trucks and cars are definitely not eatable. What's nice with this representation is that similar items are grouped together, which helps the transformer to interpret the meaning of these words. For example, the transformer now understands that trucks and cars are similar items. However, we need more dimensions because although bananas and apples are fruits, an apple might also be associated with the company that develops technology products, such as phones and computers. So, if we add a third dimension that describes how much the words or tokens are associated with technology, we can now separate the two words banana and apple, where the word apple gets a high technology score, whereas the word banana gets a low score. The GPT-3 model had about 12,000 embedding dimensions and 50,000 tokens. So, where do these values come from? Well, transformers are trained on large amount of text, and during the training, they learn to associate eatable things with fruits and that cars and trucks can move things. These values are actually weights that the network learns to optimize in order to correctly predict the next word. Suppose that you would predict the next word in this sentence. I guess you predicted the word apple because it fits the context. The word that you paid most attention to was probably eating, because the predicted word should be associated with something that we can eat. The color of the item that is eaten also helps to predict the next word. If we were to change this word from she to he, that would not change our prediction, which means that this word is less useful to predict the next word. If we change the word eating to wearing, the prediction would now change completely. Other words may now fit better. The color does not here help us much to predict the next word. So, to predict the next word in a sentence, we pay more attention to certain words, which is exactly what a transformer is all about. Training a transformer involves a target sequence that can be seen as a true sentence from a given text. If the transformer happens to predict the incorrect word, it will update its trainable weights using backpropagation, which means that it corrects its error so that it predicts the correct word or token. This is done on thousands of words and sentences. Suppose that these are all the words that we have to build a sentence with, and that these two embedding dimensions represent food and clothes. For example, apple is highly associated with food but not with clothes, whereas the opposite is true for the word shirt. Note that 0 here means no association with embedding dimension. So, if a transformer were to predict the next word in the following sentence, it would extract these rows from the embedding matrix with the words or tokens that are included in the sentence, so that we have the following reduced embedding matrix. So, this will be our input to our simplified transformer that has already been trained to predict the next word. When we use a trained model to predict, this process is called inference. Next, we should add positional encoding to give the transformer information about the order of the words in the sentence. A simple way to include positional encoding is to create a matrix of the same size as the extracted embedding matrix and place increasing numbers in this matrix, and simply add those numbers to the embedding matrix. A more common way is to compute the positions based on sine and cosine functions, but there are a number of ways to do this. This is just one method, since we only have two embedding dimensions in our example. An I starts at 0 and is increased to 1 for the second embedding dimension. The exponent will here be equal to 0, which means that we can simplify the equations of the positional encoding like this. So we plug in position 0 and compute the values. Then we plug in position 1, 2, 3, and 4. We will now add these two matrices, so that we get position-aware embeddings. For example, 0.2 plus 0.14 is 0.34. We'll now compute the attention matrix, which starts by computing the Q and K matrices based on the position-aware embedding matrix. So, to compute the attention matrix, we multiply the position-aware embedding matrix X by a so-called Q-weight matrix to produce a query matrix or Q matrix. To multiply these matrices, we do a dot product, which means that we multiply the values in these elements, and then these elements, and then sum these two products. Then we continue to the second row and do the same calculations. Note that since these weights happen to be 1 and 0, the first embedding dimension is identical to the new feature dimension in Q. This new feature dimension therefore represents association to food only. And since these weights happen to be 0.5, the second feature dimension can be seen as an equal mixture of food and clothes. These values are optimized during the training on a large amount of text, so that the transformer predicts the next word as good as possible. Note that these weights are fixed, which means that they are used for all types of input sequences during inference, after the network has been trained. The Q-weight matrix may actually have a different number of columns than the embedding matrix, which will produce a query matrix with a different size than the position-aware embedding matrix. The GPT-3 model had 12,288 embedding dimensions, so it would have had this size for our simple example. And the Q-weight matrix would therefore have 12,288 rows. The Q-weight matrix for a single head attention had 128 columns in GPT-3, which would therefore produce a query matrix of 5 times 128 in our example, because our sequence length is 5 and the number of columns in the Q-weight matrix is 128. For example, These dimensions represent the original position-aware embedding dimensions of food and clothes, because the Q-weight matrix happened to include these numbers, whereas this dimension represents an equal mixture of the two embedding dimensions, because the values of these two weights are the same. Anyway, to keep things simple, we use just a 2x2 matrix in this example. Note that by multiplying the Q-weight matrix by matrix X is the same as using a linear fully connected or dense layer with the following weights. If we plug in these two values here and compute the weighted sums of the embedding values for the first token, we'll get the values of the first row of the query matrix. Then we take the next row and so forth. To produce the attention matrix, we also need to calculate the key matrix. Let's use this K-weight matrix with the following made-up weights. If you multiply the K-weight matrix by the position-aware embedding matrix, we will get the key matrix, which again can be seen as we use a linear fully connected or dense layer. We will now multiply Q by K. So these are our Q and K matrices. To multiply these matrices, we need to take the transpose of K, so that it looks like this, where its previous columns are now presented as rows. Multiplying Q and K gives us the following matrix. For example, this value is calculated by multiplying these elements and these. This follows the same concept as how a similarity matrix is calculated based on the dot product. If you like, you can try to multiply the embedding matrix with its transpose to see what you get. The advantage of involving Q and K is that it includes trainable weights, so that the model can learn more about the attention. Next, we scale the matrix, which is done during the training process for numerical stability, by dividing the values in this matrix by the square root of the feature dimensions of Q and K, which is 2 in our example, so that we get these values. Next, we apply causal masking by setting the upper triangle of the matrix to infinitely large negative values. I have here set these elements to -1 billion. In a decoder-only transformer, we like to apply a causal mask to prevent tokens from attending to future tokens. I will explain what this means after we have applied the softmax function. Next, we apply the softmax function. This is the softmax function that we will apply to every row. So, if you plug in this value here, and all the corresponding values in the denominator, and do the math, it will result in the value 1 that we plug in here. Then we apply the softmax function to the other values in this row. Once we are done, the values should span between 0 and 1. The values on each row should also sum up to 1. Then we apply the softmax function on the other rows, which will result in these values. So, when we apply causal masking, we make sure that the token only attends to itself and the previous tokens to predict the next token. This explains why the token eating has non-zero values for these tokens and 0 values for these tokens. The token eating will therefore pay no attention to the words or tokens that come after. So this is our attention matrix, which is used to determine how much each word in a sentence should focus or attend to every other word to understand the context of the sentence. The rows represent the query, whereas the columns represent the key. So you should read from left to right. For example, this row shows how much the token eating attends to itself and the other tokens. Since this token attends to other elements of itself, this is sometimes called self-attention. For example, the token eating is focused on itself, and mainly on the word she. Similarly, green is mostly focused on and itself. However, note that I have used made-up weights in this video, so don't pay too much attention on the exact values in this matrix. So, we are approaching the end of the attention block, which involves the computation of the so-called value matrix. We will multiply the value matrix by the attention matrix. To compute the value matrix V, we multiply the weight matrix V, which includes these 4 weights, by the position-aware embedding matrix. We are now ready to multiply the attention matrix by matrix V, which will result in the so-called context matrix that includes contextual embeddings. Note that this matrix looks very similar to our previous position-aware embedding matrix, but now also includes the information about the attention. For example, this value comes from the following calculation. Next, we will apply this residual connection, which means that we will add the position-aware embedding matrix with the context matrix we just computed, so that we get the following matrix. By doing so, we restore some of the information from the positional-aware embedding matrix that might have been lost in the attention block, and also facilitate the optimization process during the training. Note that these matrices have to be the same size in order to add them. If the context matrix would have, for example, 3 dimensions, because we might have used weight matrices with 3 columns, then we may use an output projection matrix with 3 rows and 2 columns, which we multiply with the context matrix, so that we get a context matrix with the same size as the position-aware embedding matrix in order to add these 2 matrices. The output projection matrix is especially useful when we have several attention heads that needs to be compressed to the same dimension as X. It is now time to normalize this matrix, which is done to stabilize the computation during the training. This means that we subtract the mean from these values so that we get centered values around 0. And then divide the centered values by the square root of the variance plus a small constant to avoid the possibility of dividing by 0. We will by this standardize the values. This calculation also includes trainable weights that help to stabilize the computation. However, we will not include these here. These are our normalized values. Since we only have 2 feature dimensions, the normalized values will either be -1 or 1. Using only 2 embedding dimensions is therefore not a good idea, because the normalization then removes a lot of information in this case. We will therefore skip the normalization and instead use these values as input to the fully connected layer. So, in order to predict which word that comes after green, we plug in its corresponding values in the fully connected layer. These values contain information about the embedding, the position, and the attention. If we want to predict what comes after eating, we would instead plug in these values. Remember that the first feature dimension of the original embedding matrix was associated with food, and that the second embedding dimension was associated with clothes. It would therefore make sense that the network has a low or negative weight that is associated with the connection between clothes and apple, and a high weight between food and apple. This is a bias weight that is also optimized during the training. Then we compute the output value for apple by using the bias weight, the input values, and the weights that are associated with the output node apple. Then we do the same calculation for the output node shirt. It would make sense that the network has optimized the weights so that food gives a weak signal to shirt, whereas clothes gives a strong signal. Suppose that we would get these values, called logits, for all the output nodes. Note that the calculations of these numbers corresponds to this matrix operation, where X is the following matrix, and this is the matrix with the weights associated to the connections between the input and output nodes, whereas this is a vector with the bias weights. Finally, we plug in these values into the softmax function to compute the output probabilities. So, if we apply the softmax function on these values, we'll get these probabilities. Since the highest probability is associated with apple, the model will predict that the next word is apple. Suppose that we would shift these weights. Then the model would instead predict the word shirt. Since the model trains on target sequences, it will try to increase this probability to make the correct prediction by changing the values of these weights and all the other weights in the model, including the weights in the Q, K, and V weight matrices and the weights in the embedding matrix. Although we use a very simple example, the network has 24 weights to optimize in this layer. 2 weights each for gamma and beta because we have 2 feature dimensions. 12 weights to produce the Q, V, and K matrices, and 16 weights in the embedding matrix. So, in total, our simple network has 56 weights to be optimized during the training. When we use the network for predicting the next word after the training is done, the values of the 56 weights are fixed. However, the attention weights in the attention matrix are not fixed, because these values are recalculated depending on which sentence we plug in into the network. Finally, we will have a look at one method that produces more variation in the output, which is called top P sampling. Instead of selecting the word with the highest probability, it can sample from the smallest set of words or tokens whose cumulative probability is greater than P, which can, for example, be set to 0.75. The method might here, due to chance, therefore select the word hat. By randomly selecting among the most likely words, it will produce a larger variation in its output. This was the end of this video about transformer neural networks. Thanks for watching.